Welcome everyone to the machine learning sessions. In this session, we are going to learn about random forest. The learning objectives of this session are: what is ensemble modeling? What is bagging? We'll learn the random forest algorithm and then many concepts related to random forest, out of bag error rate, overfitting, how to eliminate overfitting by finding optimal number of trees and optimal number of variables to select, and finally evaluating how good our model is using various model performance measures. So let us quickly jump to the concept of ensemble modeling. Ensemble, it is use of multiple machine learning algorithms to obtain better predictive performance. The first statement, use of multiple learning algorithms. What it means is, to solve a given problem statement, we are going to use multiple algorithms. To solve a simple 1-0 kind of a problem statement where our target is binary dichotomous, which means our target has got output like 1 or 0 or output like responder or not responder, there are many machine learning training algorithms. You can use artificial neural network, you can use support vector machine, you can use random forest, you can use gradient boosting machine, logistic regression, naive Bayesian, k nearest neighbor, and so forth. So here the point is, you use multiple learning algorithms, which means you will use, say, 5 techniques. Let us say the 5 techniques that we are using is naive Bayesian, k nearest neighbor, random forest, artificial neural network, and logistic regression. In that case, to solve that problem, you are using 5 modeling techniques, and you will use the output of these 5 modeling techniques to predict the final outcome, such that the output given by using multiple learning algorithm is better than what you would have got by using individual constituents of the ensemble. Which means if I would have used only artificial neural network, my model performance would have been relatively weaker or relatively poor compared to my model performance when I have used all the 5 machine learning techniques together in the ensemble. So this is the concept of ensemble modeling. Let us now try to understand another concept which is called bootstrap aggregation. Bootstrap aggregation is also called bagging. Bagging is basically an abbreviation for bootstrap and aggregation. What is bootstrap? When I have data and I'm doing sample, I'm generating sample from the data such that I'm doing sampling with replacement. What do you mean by sampling with replacement? Assume you have got 100,000 records and you have to create a sample of 10,000 records. And now these 100,000 records are numbered as 1, 2, 3, 4, 5, 6, ... 1 lakh. From this, you have to randomly select 10,000 observation. You randomly select one of the observation and say the observation number is 5. You make a copy of that observation number. In the population, when you are now going to draw another record, the population will still remain 1 lakh, which means record number 5 will also be here. So when you are drawing a second record, it is quite possible there is a chance of the second record being again 5. Which means a given record can be selected multiple times. This is called sampling with replacement. In case of sampling without replacement, what happens is, once you have selected a record, you made a copy, that record is out of the population. Now you cannot select that record. That is called sampling without replacement, because you are not again putting it back in the population. Okay, this is the difference. The process of doing sampling with replacement is called bootstrap. This approach of sampling is called bootstrap. Okay. In a random forest algorithm, what happens is when you call the algorithm, you have to specify how many classification trees you would like to create in the background. So when you are calling a random forest function, one of the parameters you have to pass is number of classification trees you would like to create. Let us say we give a parameter 51. And when you're calling the algorithm, you have to also pass a data set on which you wish to build the model. That data set, from that data set, what you're going to do is a first step, you're going to create 51 samples with replacement. When I'm saying 51 samples with replacement, I'm not saying that each sample will have 51 observation. What I'm saying is I passed the data set which has got 1 lakh observation. So I'm now going to create a sample with replacement such that the sample with replacement will also have 1 lakh observation unless you specify the sample size. If you specify the sample size, in that case you will create a sample with replacement which is equal to the sample size. But if you do not specify the sample size, in that case sample size is equal to population size. So first step, you are going to create 51 such samples with replacement. Now I have got 51 samples. On each of the 51 samples, you are going to build a classification tree model. Again, there will be some randomization which will be there in selection of attributes, in selection of features which are used for the model development. We'll see all of those things later, but for now, step 1 is I have to create 51 samples with replacement. On each of the samples, I have to build a classification tree. So now I'll get 51 classification trees. There is a new record for which I wish to predict the output of that record, whether it will be 1 or whether it will be 0. This new record will now be subjected to 51 classification tree. Each of the classification tree is going to give a prediction for this new record whether it will be 1 or 0. Assume 27 trees say it will be 1 and 24 trees says it will be 0. Majority out of 51 is saying it will be 1. So the final outcome will be considered as 1. That is, based on majority rule, you will decide the final outcome. In case I do not want the output to be 1 or 0, but I want what is the probability of the new record being 1. So in that case, what will happen is this new record will be predicted by 51 trees, and 51 trees are going to give me 51 probabilities. I'm going to do average of these 51 probability and assign it to the new record. That will be the probability of the new record being 1. So if you see in a bootstrap aggregation, as a first step, what we are doing is we are sampling with replacement. After doing sampling with replacement, on each sample we are building a classification tree model, and the new record, the way it is scored is you predict the outcome for the new record by the number of trees, and then you aggregate the output of those trees to get the final prediction. So it's a two-step process. One is a bootstrap sampling, second is the aggregation of the outcome, and together bootstrap aggregation is termed as bagging, and random forest technique makes use of these two concepts of bootstrapping and aggregation of the outcome. That's why random forest is also called a bootstrap aggregation technique, that is a bagging technique. Random forest, it's an ensemble modeling technique by itself. Why it is called an ensemble technique by itself? What was the definition of ensemble modeling? Use of multiple learning algorithms. However, in a random forest technique, we are not using multiple algorithms, but what we are using is same algorithm multiple times to create multiple trees. So in a way, it is a standalone ensemble technique. Okay. Random forest involves construction of multitude of decision trees at the training time, which means we have to create multiple decision trees. Prediction is based on mode for classification tree and mean for regression tree. What it means is, in case I have to predict a class, in that case I'll have to see what class has been predicted by majority of the trees. If majority of the trees says the class is likely to be A, then the final outcome would be A. If majority of trees say the output is likely to be B, in that case the final outcome will be B. That is called the mode principle. In mode, what you see? Majority. In case the outcome is a continuous number, in that case what you do is you take average of all the predicted outcome values. So that is used in regression. Let us now try to understand the machine learning, the random forest 3-step process. Step 1 of random forest is sampling with replacement. So here what I have shown is there is a data set. What you want to do is pass a parameter saying that I would like to have 21 trees. Now how do you decide whether you want to have 21 trees or 51 trees or 501 trees? That is basically a process of finding out what is the optimal number of trees we require for the model development. For now, let's go with the flow and say I would like to have 21 trees, and I have passed this data set to my algorithm. The step 1 which the algorithm is going to do is, from this population it is going to create 21 different data sets, D1, D2, D3, D21. How are these data sets going to be created? Sampling with replacement. The default implementation is, if you have in the data set which you are passing to the model algorithm function, if you have say 20,000 records, each of the samples will be 20,000 records. But those samples will be created by sampling with replacement. Step 2 of the algorithm will be to build a model on each of these data sets. So let us now consider data set 1. And let us assume the number of features, number of attributes that we have are 100 attributes. Let us call them as A1, A2, A3, A ... A100. We have to build a classification tree on it. Now to build a classification tree, what would happen is, in a typical classification tree, all 100 attributes will be evaluated for the Gini gain or for the information gain, and the variable which gives you the highest gain, that variable will be used for splitting the data into 2 child. Again, there is a randomization in a random forest technique. The randomization here is, you are not going to evaluate all 100 variables for the Gini gain or the information gain. Whichever technique you are using CART technique, or you are using C5.0 technique or C4.0 technique or the C4.5 technique. You have to pass a parameter to the function, saying that I would like to consider only 10 attributes out of 100, which means at the root node, when I'm working on the dataset 1, D1, instead of evaluating all hundreds for Gini gain, I'm going to take only 10. Again, these 10 attributes will be randomly selected. 10 out of 100 will be randomly selected. Only 10 will be evaluated for Gini gain. The variable which gives you the highest Gini gain will be considered, and you get the 2 child. So here in the diagram, here we have got 2 child. Now in left child, once again, out of the 100 attributes, you're again going to randomly select 10. You're not going to bother about what 10 was selected in the previous iteration. You're going to take random 10. Out of the random 10, again you are going to find the variable which gives the highest Gini gain, and that node will be further split. Likewise, the right child, out of 100 attributes, you are going to select random 10. You are not going to be bothered about which 10 were selected in the above parent node or the beside left child node. This process will be independent selection. So you select 10 independent variables randomly, evaluate Gini gain, the variable which gives the highest Gini gain will be considered, and that child will be further split, and this process will keep repeating till the stopping criteria is met. This is how the first tree of the random forest be created. Now for the second dataset D2, you are again going to repeat the same thing. You are not going to bother about which were the 10 variables selected at the root node level in the first dataset. The second model on the second dataset will be an independent process of the first dataset. So again, a random 10 will be selected. You will find the best Gini gain, split, you get child nodes, again random 10, and this process goes on for dataset 2 till stopping criteria is met, and then for dataset 3, 4, 5, ... dataset n. This is how you create n classification tree models. Now the choice of selecting number of attributes, that is 10 or 12 out of 100. How do you arrive at this number 10 or 12? Thumb rule is, if you have got 100 attributes, take a square root. And that square root is the number of attributes you should be considering. That is a thumb rule. Okay. Again, using some randomized search approach, we'll find out the optimal number of m to be considered, number of variables to be considered. That we'll have through a systematic process. But if you have to go through a thumb rule approach, in that case, square root of the number of attribute is what you should be selecting. Okay. The final step is, based on your n samples, n data sets, D1, D2, D3, Dn, you have built n classification trees. Each record is now classified based on n trees. The final class of each record will be decided based on voting principle, that is the mode principle. If majority of the predictions comes out to be class 1, final outcome will be class 1. If majority of the predictions comes out to be class 0, final class will be class 0. In case if it is a continuous number, that is like you want to predict the probability, in that case you classify each record based on the n trees, you will get n probabilities, and then you have to do average of those n probabilities. That will be the final probability. This is the step 3. In random forest, you do not have pruning step. There are certain original papers on random forest technique. What they suggest that the error, the classification error of a random forest model depends on two parameters. Depends on two factors, not two parameters, depends on two factors. The factor is what is the M that you select. If you select M too small, in that case what may happen is your trees may not be strong. And if you select M too large, in that case what may happen is your trees may be highly correlated. So we have to now understand how to find the optimal M. Selection of the number of variables out of the total variable is a very important factor. If you select it too small, in that case you may end up with a weak models. If you select too large, you may end up with highly correlated trees. In that case you do not require so many trees. You could have done with one tree only. So let me try to explain this concept. Assume you have got 100 attributes. You may want to you may want to use your pen and paper to note down the things. Assume you have got 100 attributes. Out of the 100 attributes, let us say 75 attributes are weak, 20 attributes are moderate, 5 attributes are strong. I repeat, 100 attributes, 75 weak, 20 moderate, and 5 are strong. So the solution would be something like this. In our old data, we have got 5 strong variables, 95 weak or moderate variable. We do the first draw. Probability of not selecting a strong variable in this case would be 95 by 100. We do a second draw. Assuming the first draw, we did not get a strong variable. In the second draw, the probability of not getting a strong variable will now be 94 by 99. Assuming in the first and the second draw we did not get a strong variable, the probability of not getting a strong variable in the third draw also will be 93 by 98. Probability of not getting a strong variable in all the three draws in that case will be equal to 0.95 multiply 0.949 multiply 0.948. So the probability of getting at least one strong variable will be equal to 1 minus of 0.856, that is 0.144. What it means is, if I consider only 3 variables to build a model, there is only 14% chance of a strong variable being selected. Now assume I am building 100 classification models as part of the random forest in the background, and each model is one level depth. Max depth is only one level. What it means is 14% of the trees will have a strong variable splitting the root node, and remaining 85.6% of the trees will not have a strong variable splitting the root node, which means 85% approximately of trees will be made of weak variable or a moderate variable. My final decision in a random forest is done based on voting. So voting will happen out of the 100 models, and out of the 100 models only 14 or 15 models are strong. A good chunk of models are weak. So my overall outcome is likely to be a weak model. This is what is going to happen if the number of attributes that you are randomly selecting is kept too low. Now let us take another scenario Out of the 5 strong variable, let us say variable X is the strongest. And we are now going to select 95 attributes out of 100 for my model development. And model will be 1 level depth only. In that case, because we are selecting 95 variables out of 100, X is the strongest of all the variable. Chance of X being selected will be 95%. And if X is selected, then X is going to be the best variable out of the 95. That's why most of the models will have X variable coming as a separating variable, splitting variable. In short, 95% of the trees will have X variable coming at the root level, splitting the tree. In other words, 95% of the trees will be same. If 95% of the trees are same and our decision is based on voting principle, there is no point of doing any voting because majority of them are same models. In that case, I do not require so many trees. It would be good if I build only one tree. What we are trying to understand is too small m and too large m. That is, number of attributes that we are selecting out of the total should not be neither small neither large. Somewhere optimal is what we'll have to select, and that optimal we'll have to find by doing some grid search cross validation or by doing some randomized search cross validation approach. These are the 3 points which the research paper says. Let me just read it out. Research paper says the correlation between any two trees in the forest. Increasing the correlation increases the forest error rate. If more trees are same, they will point in the same direction, which means there will be a correlation error. Strength of the trees influences the final outcome. Now, strength of the trees depends upon whether you are taking few variables or more variables. If you select more variables, your strength will be higher because good variables will have chance to come. But if you take more variables, what will happen is same variable may come in all the models, which means all the models may become correlated. High correlated models, in that case, you do not require many models. You can do work with one model also. Okay. So too high M will lead to high correlation between the trees. However, too small m will lead to weak trees. One side I want to have strong trees, on other side I want trees should not be correlated to each other. So we need to find the optimization between correlation and strength of the trees, and somewhere in between we'll have our optimal m. This is the concepts on random forest algorithm. Now we will see how to go about building random forest model in Python. We will do the building of random forest model in Python in our upcoming session. Thank you.